going to be going over questions 6 to 8 in the machines test of the Sierra Vista Invitational presents Olympiad. So the question reads, an inclined plane has a length of 5 meters and an inclined angle of 25 degrees. An object of 4.5 kilograms starts at rest at the top of the plane. The first question is asking, what is the IMA of the plane? So if we have an inclined plane that's like this, and the length here, let's just call this length L, this length H. The L is along the incline and H is the height of it. And the IMA is simply the length over the height. And I know that we're given that the length is 5 meters. And we're not given the height value, which is what we're trying to solve for. And we're also given the inclined angle, which is this angle here, which is 25. And how can we find H? Well, we can find H through trigonometry. So if we take sine of theta, which is 25, basically it'll give us what value? It'll give us H over L. So, and then this is essentially sine of 25, and we're solving for H, so H will be L times sine 25. And essentially we can just plug it in here, because we don't need to set that L is equal to 5, because L will anyways cancel out here, as you'll see. So L over L sine 25. Now the L's cancel out, and you'll be left with 1 over sine of 25. And 1 over sine of 25, and then if you plug that into your calculator, that'll give you a value of 2.366. And that's close enough to answer choice C, and they rounded the value to 366. Okay, on to question number 7. Oh, and also one more point to point out is that the IMA or the ideal mechanical advantage of an inclined plane is going to be equal to 1 over sine of theta. And this is because if you write this out, like the H as we showed here, if the H was written out as L times sine of theta, it's essentially just L over L's sine theta. But then the L's cancel, so you're just left with 1 over sine theta. So that's another quick and easy way to find the IMA of an inclined plane. Okay, on to question 7 now. Assuming that the surface of the inclined plane is frictionless, how long will it take for the object to reach the bottom of the inclined plane? So we're asked to solve for the time it'll take. So to solve for the time, we have to use kinematics. And to use kinematics, let's first think about forces. And what can we use about forces? Well, we can use Newton's second law, which is sigma F is equal to ma. So this net force is equal to mass times acceleration. Well, let's draw a force diagram on what's going on in the inclined plane. And what are the forces that are affecting its journey down the incline. So you have something like this. angle 25, and then you have this object here. So as it's going down, you have this normal force, but that's perpendicular to the plane, and that doesn't affect its motion down the plane. You have the force of gravity, and then you have the gravity components. So you have one. Let me do the gravity components in a different color. So you have this force of gravity, this force, and or I'll just draw it like this. One like this, one like this, and one like this. So one of the forces, if you can see, is perpendicular to the inclined plane, and one of them is parallel to the inclined plane, and one of them is straight down from the object. And so if you can see here, I'll just make this a little bigger. This value is theta or 25, and by some trigonometry you can figure out that this is the actual force of gravity, this one right here, and it points straight down, and that's equal to mg. And then this one parallel to the incline is going to be equal to mg sine theta or 25. And then this one right here. Oh wait, I'm not sure why I drew it like that. Let me change it. It's actually perpendicular to the incline, so something like that. And this is going to be how the value of mg cosine theta. Okay. So what is the thing that we're looking for? We're looking for the one that's parallel. We're looking for the one that's parallel to the incline, because that's the one that's going to affect its motion down. And that's the only force that's parallel to the incline. So we can add that. So that's the only one that's in the delta F. So that's mg sine theta. And that's equal to mass times acceleration. The m's cancel out, and g is 9.8 times sine of 25. That's the acceleration. And if we solve that out, we'll get a value of about 4.14. And now that we have the acceleration, let's try to use some kinematics. So what values do we know? Well, we know that we just found out that we know the acceleration. We also know delta x, which is the total distance that it covers, or the displacement. Sorry, not the distance, the displacement. And that's this value here, or 5. And we also know the initial velocity that it starts out with, because it said the problem said that it starts at rest at the top of the inclined plane. And what are we solving for? We're solving for the time. So we should use the kinematic equation of delta x equals to v naught times time plus 1/2 at squared. So delta x is equal to 5. So actually the v naught times time cancels out, and that's actually, yeah, because it's 0, because v naught is equal to 0 because it starts out with 0 velocity, and then this is going to be equal to 1/2 times the acceleration, which we found out to be 4.1417 times the time squared. Solving for the time squared, we get that it's equal to 2.414, and that the time is therefore going to be equal to 1.5538. And this most closely matches the answer choice of A. Okay, let's now move on to the last question, which is question 8. The question reads, now assume that the surface of the inclined plane has a coefficient of kinetic friction of 0.33. What is the work done by friction on the object as it moves down the inclined plane? So we have the coefficient of friction as 0.33, and we're asking for the work done. So in this case, the work done is equal to the force times the distance. And this is for the coefficient of, this is for the kinetic friction, the force of kinetic friction. And to solve, let's first solve for the force of kinetic friction, and that's going to be equal to the normal force times the coefficient of kinetic friction. And let's first try to find out what the normal force is going to be. So if you have the same diagram of the block, the normal force is good. It's a bit messy drawing. So the normal force is going to point directly up, perpendicular to the surface of contact. And if you look at if you break stuff up, the components of gravity, like we did above, is essentially the same diagram. We want the component of gravity that's perpendicular. So the one that's perpendicular in this case would be this one, and that one, if we scroll up, is it has the value of mg cosine of theta. So the normal force is going to be mg cosine of theta. And then we know that the coefficient of friction is going to be 0.33. Okay, let's just plug in all the variables that we know. And so this is going to be 9.8 times 4.5 cosine of 25 times 0.33. Now if you plug this whole expression into your calculator, you should get a value. You should get that the normal force is equal to 1.968, and that and then we could just multiply that by the coefficient of friction. And when we get to this, we get that the value is 13.189. Okay, that's the force of friction. And now we'll just plug it into the work equation. So work is equal to force times distance, and it's going down actually. So depending on whichever way it's moving, the force of friction opposes that. So anyways, the work will be negative. And since we're considering that the force of friction is positive, then the distance traveled will be negative, or the displacement will be negative, because the displacement will be in the opposite direction of the force of friction. It'll oppose the motion. So we'll take the distance to be -5 because it's going -5 to the direction of the force of friction, which we're taking as positive. So 13.189 times -5, and that's equal to roughly -65.945. And this is our answer. And let's check if it matches one of our answer choices. Yes, and it roughly matches B, which is a rounded version of this equation. So thank you for watching, and I'll be providing more astronomy and physics content along the way. Thank you.